what I said is that I'm going to talk about this phenomenon in statistical mechanics that is known as order by disorder. And it's an interesting effect where you have a large degeneracy of the ground states, but at zero temperature, of course, you might find yourself in any of these ground states since they all come with the equal energy. But at a small but finite temperature, the system might prefer the states which have a large space of low energy excitations nearby. So you can think about this as free energy taking the place of energy, and the free energy, of course, cares about entropy as well as the energy itself. And so if there is a subset of ground states where which come with the whose nearby excited states provide enough entropy, these states will win. There is a quantum version of the same effect. And in the quantum version of the same effect, it's not thermal fluctuations, but rather quantum fluctuations that provide the selection for you. And if you want to think about this in quantum terms, what you should think about is the classical energy comes with quantum corrections that you can think of as the 0-point energy of your harmonic modes. And of course, so there is no free energy in this case. You just think in terms of energy, but it's quantum corrections that select some subset of states. So that's just explaining the title of my talk, at least partially. And this is something that has been done in collaboration with. So I started this project with my graduate student at that time, Jackson Pitts, who has graduated last year. And then it turned out that Simon Trebst from the University of Cologne gave the same, roughly the same project to his graduate student, Finn Lasse Bussen, who is now a postdoc in Toronto. And in the process, we also talked quite a bit to Roger Mössner, who is the Max Planck Institute in Dresden. And so as a result, sort of this project has been pursued by various parts of it by various members of this collaboration. And so I'll tell you about the results. But so, okay, I told you what order by disorder is. Now I need to tell you something about the other words in this title, and that is the Kagome and chiral interactions. And so let's just go and let's hope that I have some control over my laptop. And I'm not sure. I can't scroll the page. I'm afraid. Oh, well, let's hope this will work. So I don't know how to operate this thing without buttons. I succeeded somehow, but okay, let's hope this works. I'm not sure what I did, but it worked. So first thing first, what is chiral Hamiltonian or chiral interactions? So what I mean by the chiral interactions is the following term in the Hamiltonian. This is the triple product of spins, and you should think of them for most of the Stokes classical spins. So unlike the normal Heisenberg term, which is just a dot product of neighboring or whatever interacting spins, this one is the triple or the mixed product of three spins on a triangle that you somehow define on the lattice. And one thing about this Hamiltonian is that it clearly breaks time reversal symmetry, because if you the time reversal flips the directions of the spins, and so this term changes sign. On the other hand, what it doesn't, it's actually, no, this is unbearable. I'm not sure I can progress my talk like this. Let's try. If it doesn't work, I would have to reboot, and that would kill the Zoom. But yeah, so under normal circumstances, if you define a term like this, what you want to have is you want to have lattice that has triangles. And the lattice that I'm interested in is the Kagome lattice that is made of corner sharing triangles. And the fact that triangles are corner sharing will be important for us. So as I said, it consists of corner sharing triangles. And those of you who have never seen the word and think it's the name of some physicist who invented that, I should say that it's not. And that's the actual Kagome, which is the Japanese basket weaving pattern. And that's where this came from. And as I pointed here at the bottom, it's this lattice, for the reasons I'll explain in a minute, is a fertile playground for frustrated magnetism. And I should say that with my computer troubles, I am getting into a very frustrated state myself. So I'll be on the same page with the subject of my talk. So what do we mean by frustration other than my feeling right now? That depends on whom you talk to. And normally people say that, well, a typical example of frustration would be a Heisenberg antiferromagnet with the, so antiferromagnet meaning that you do it with the positive coupling constant J, which prefers the anti-aligned spins. And if you try to put this Hamiltonian on any lattice with triangles, you see that you cannot make every pair of spins happy. And people often refer to this as frustration. But I would argue that's not necessarily a good definition of frustration. The reason for that is that the same Hamiltonian can be rewritten as, well, if we are dealing with a lattice with triangles, as the sum over all triangles on the lattice of just the total spin of that triangle squared, plus some constant that we don't care. And it's absolutely clear how you can make a ground state of that Hamiltonian. All you need to do is to arrange the spins in such a way that 3 spins of each triangle just add to 0. And so you didn't make every pair of spins the happiest, but you can make every triangle of the lattice as happy as it can be by just making the total spin, the net 0 of that triangle 0. And so the ground state, therefore, would be a state on which each triangle has 3 spins that add to 0, or they make a 120 degrees arrangement with one another. And if we try to play this game on, let's say, a triangular lattice, it turns out that you have a choice, of course, of 3 spins on one triangle of the lattice. But once you've made that choice, once you choose these 3 directions at 120 degrees to one another, now, of course, you can just rotate this triad once any way you want. But once you've made this choice, your hands are tied, because for the next triangles that border them, it's so the directions of other spins are fixed. And so whether or not you want to call this frustrated, I don't know, because you've chosen the directions of 3 spins on one triangle, and then the rest just falls out. So there is no degeneracy of ground states, which in my opinion is the hallmark of real frustration in the systems. So you only have this global rotational symmetry of that's the choice of the direction of 3 spins, and that's it.
Can you say the frustration is when the degeneracy grows like volume or something?
Or something like this, right? So what I want to do is I want to have a magnitude of ground states that is not just breaking. So this ground states breaks one global symmetry. Right. What I want is which is very common, but you know, the phenomenon I'm going to tell about today is not the most common phenomenon that you find in the world, and so that's why I said that. What you mean by frustration really depends on whom you talk to. And so for me, frustration is something like the same Hamiltonian as you've seen before, but let's say I want to put it on a Kagome lattice rather than triangular lattice. And the game is, of course, the same. For every triangle, you want to arrange the spins in such a way that they add to 0. But then you continue playing this game. And so let's put these 2 spins like this, but you could also put them like this, still works. And then you have this choice every time you want to fill all of them. And so this is one particular way of arranging the spins in this 120 degree pattern. But if you look at the, let's say on the downward looking triangles, you see that there is absolutely no order in the pattern that I there is no periodicity in what I've done to you, unlike the triangular case where all of them follow the same exact pattern. And so there is actually many of these states. Furthermore, there is absolutely no reason why all spins must even lie in the same plane. And I'll come to that in a second. But before I go there, I want to say that for the reasons that hopefully will become clear in a couple of minutes, what I want to do is I want to stop drawing arrows very soon and just put colors instead of them, as long as we have this translation between colors and directions of arrows in our head. And I want to say that there is an exponentially large number of ground states that are available to this system. You can actually, even if you want to arrange all spins in the same plane, you can, which is not mandated here. Even then, the number is exponential. You can enumerate them, but I don't want to go there now. But I want to point out the existence of so-called Weathervane modes. So what are Weathervane modes? Weathervane modes are the modes where you select a loop on your lattice, shown here in yellow. The one thing about this loop is that it only goes through the spins of 2 colors out of 3. What that implies is that the neighboring spins are always red in this particular case. So let's say the red spins are up. So what that means is that the blue and the green spins on that loop can be rotated simultaneously around the direction, the upward direction. So that was supposed to be a loop along which I performed the direction. They can be rotated by an arbitrary angle, getting them out of the plane. And but every single triangle that is affected by this still has the same property that the 3 spins add to 0. And so this is an example of a Weathervane mode that will play an important role for me. So that's the result of that just rotation by some arbitrary angle in the plane perpendicular to the z-axis. All right, so for those of you who don't know what a weathervane is, that's the Weathervane. That's another one. I found that's from some German house somewhere in Rhine-Westphalia, apparently. So that's that's their favorite. That's a dentist, by the way, in case you haven't figured that out. All right. So now what I want to say is that this shows, for example, that the spins don't even have to lie in the same plane. But it turns out, and I'll mention that in a second, that we should really think of so the coplanar states. That's the states where all spins nevertheless lie in the same plane. Play a rather prominent role in this business. And among many coplanar states, 2 are particularly prominent. And I drew them here already without bothering to draw the directions of spins. And one of them is the so-called √3 by √3 state. And if anybody can please provide some batteries, I would appreciate that. But I'm not sure I know how to do that myself. This thing is about to die.
What kind of battery?
Okay, now it works, but let's see for how long. So the 2 prominent coplanar states are the so-called √3 by √3, and that's the state. So let's just eyeball the state for a second. So one important feature of the state is that every hexagon of the lattice consists of only 2 colors or 2 directions of spins. So you see that this one only has red and green. This one has only green and blue, and so on. In particular, what that means, if you remember that each hexagon, at least taken in isolation from the rest of them, can affect a Weathervane mode because it's only flanked by the spins of the 3rd kind, and so it allows for rotating these spins around this axis. So this has a huge number, in fact, an extensive number of Weathervane modes associated with this arrangement. √3 by √3 refers to the periodicity of this state. So its unit cell is 9 spins rather than 3, which is the unit cell of the Kagome lattice, and that's just the Q corresponding to that. The other one is the most uniform state, you can imagine that's why it's called the Q0 state, where the unit cell, the magnetic unit cell, coincides with the unit cell of the magnetic lattice. So you can see that all, for example, upward-looking triangles are the same here. Now, this is another interesting case. And the reason for that is that whereas the √3 state maximizes the number of Weathervane modes available to you, this one actually minimizes them, because all Weathervane modes now, you can only affect them along the lines of two colors, and all lines of two colors now run all the way through your system. So the total number of Weathervane modes here is actually sub-extensive. It scales the perimeter of the system. And these two states, so remember them, I'll show them again, but they play a prominent role in what I'm about to say. And so one really beautiful result from the 90s of the previous millennium is that naively you would expect that, so all of these are good ground states of your Hamiltonian, but then you can ask yourself, does this order by disorder physics play any role in selecting between them? And naively you might think that, well, this state, clearly has more fluctuations around it, because basically every hexagon corresponds to something you can do for free, whereas here you clearly have much fewer such possibilities. And so you might naively think that this state should win. It turns out that all coplanar states come on the same footing as long as you do the harmonic approximation. So if you look at the energy in the harmonic approximation only, all of them are equally good from the point of view of order by disorder, and they all beat the states which have spins out of the plane. So there is order by disorder physics, and it selects coplanar states over all other ground states. I hopefully explained to you that the state don't need to point in the lie in the same plane. Now, in fact, it's not even, so I'll give you a very naive argument for why, for example, this state is as good as this state from the point of view of selection in the order by disorder mechanism. And the reason for that is as follows. So, well, you can definitely excite free Weathervane modes, like let's say you excite this hexagon. Now, if you do it here, you cannot do it in the neighboring hexagon simultaneously, right? Because this would require rotating spin along the c-axis, and this would require rotating spins along the b-axis, and then the spin A that is shared by both hexagons doesn't know whether it wants to rotate around the c-axis or around the b-axis, and so that's clearly there's a contradiction. So if you wanted true Weathervane modes, you would only have to do it on every third hexagon. That's allowed. This one is even worse because, as I said, there are only lines of spins, but none of that matter in the harmonic order. It turns out that in harmonic order, there is the number of harmonically soft modes. Harmonically soft means that the modes that instead of quadratic energy with respect to the rotation of spins, they have only quartic energy in the rotation of spins, is actually equal to the number of hexagons in your system, and it's the same here and here. And in order to understand this, let's actually try to visualize what happens when you try to excite, let's say, two incompatible Weathervane modes. Let's say this Weathervane mode and this Weathervane mode. And as I said, the spin A doesn't know whether it wants to be rotated around the c-axis or around the b-axis. But if you want to think about this, not really in terms of free rotations, but in terms of what happens when you expand things to the quadratical world in the orders in this degree, you see that whether or not you try to rotate the spin along the, let's say, c-axis or b-axis, in the lowest order, all that spin does, it simply pops out almost perpendicular from the plane. The distinction between whether you're trying to rotate that around the c or b axis is actually quartic in the angle by which you are trying to rotate it. Because as I said, the first inclination is to for that spin is just to get out of the plane. Everything else is small deviations from that point of view. And the same logic actually works for all of these coplanar states, irrespective of which one you choose. Now, this is probably a little bit too simplistic of an explanation, but it's actually true. So that's for that reason, as I said, people have found this rather interesting result is that the coplanar states beat everything else, but then beyond that, at least in the quartic approximation, they are all, well, in the approximation doesn't look beyond the, so these modes have zero energy in the quadratic approximation, and so they all acquire energy in the quartic approximation, so they are harmonically soft. So you need to look at whether or not the quartic energies are different in order to see if there is any discrimination between different coplanar states. Now,
do we not look at it as a quantum Hamiltonian, the semiclassical?
Right now, I'm looking at a perfectly classical case. This is perfectly classical case, and I'm just asking myself with this Hamiltonian when I'm trying to excite so if a Weathervane mode costs exactly zero. Now try to do two incompatible Weathervane modes in the neighboring hexagons. That cannot cost zero energy anymore because you are trying to do something incompatible. But then you ask yourself, well, is the energy that you are paying, given the Hamiltonian, given that classical Hamiltonian that I gave you, what is the energy, how does it depend on the angle by which you're trying to rotate? And my claim is that there is no quadratic term, there is only quartic term for this. And the reason for that is something that I tried to explain, probably not particularly eloquently, but that's the, so we'll come back to the semi-classical story later. Right now, it's perfectly classical. So this effect, the selection of coplanar states, actually has a simple consequence that people looked at, and that is you can see this effect in the specific heat per spin. So if you think that your spins are completely disordered, you would expect that the specific heat is what it is. The equipartition theorem tells you that you're supposed to have kb over 2 per degree of freedom in your system. Each spin has 2 degrees, 2 rotational degrees of freedom, so you would expect kb per spin, and that's not what you see, and that's what you kind of see at the temperatures that are low but not too low. And if you lower the temperature just a little bit further, this thing goes down, and that's just the zoom into that to a different value, which is 1112. And what this 1112 is indicative of is the fact that you have one harmonically soft mode per hexagon. And by harmonically soft, I mean what I mean. So it doesn't have quadratic energy. Its energy is quartic in the angle by which you rotate it. Now, the number of hexagons is the same as the number of unit cells. So since every spin is shared by 2 hexagons, you can really think of 3 spins per hexagon. And so out of these 3 spins, you have, so 3 spins would give you what, 6 degrees of freedom? 1 degree of freedom is actually quartic. And so the specific heat is 5 normal degrees of freedom that give you 1/2, and 1 quartic degree of freedom that gives you 1/4. And so when you add them, you get 12/5. And so the fact that your system now chooses this coplanar state is, or any coplanar state for that matter, is, so this is the hallmark of the fact that you go from a disordered state to a state at a finite, very small energy. So now we are talking about, you see that this is the ratio of temperature to J. So the temperature is finite, but very, very small. And now you have this selection. This is the order by disorder effect, and that's its manifestation in the specific heat. Now, there is some story about whether or not if you lower the temperature even further, whether there is any selection. So whether, I mean, if you go beyond the harmonic order and start asking yourself which states are preferred in the higher orders, there is some indication that √3 by √3 state eventually wins, as sort of your intuition might suggest. But that's, I mean, that is so it requires really heavy numerics, and I wouldn't say that it has been fully sorted out. Now, let me go to the, having wasted half of my time, well, hopefully that, this was actually an important introduction, because what I'm going to tell you about now, which is the actual subject of my talk, will have many, many references back to the example that I've just considered. So if you have any questions about just the Heisenberg model and the Kagome, ask them now, because I think that's a good place to see if what I just told you about has made sense. Well, okay, everybody's quiet, so let me now look at the Hamiltonian, which I'm actually going to look at. And it's a little bit more complicated than the Hamiltonian I've written originally, which only had the chiral term in it. So I want to have two chiral terms, which in principle I am, the way I've written it like this is that I want to consider a situation where the chiral terms have the same sign or the opposite sign on the upward-looking and downward-looking triangles. And if it has the same sign for both of them, then I would call this model uniform chiral model. And if they have opposite signs, I would call it staggered chiral model. And then in principle, I might also want to mix in a Heisenberg term on top of that. And so you see that depending on this parameter lambda, I can get all these cases. So lambda equals 1, these terms come on the same footing. And so this uniform chiral model, this term of course vanishes. Then if lambda is equal to 0, then these terms vanish and you only have the Heisenberg model. And then if this parameter lambda is -1, then these two terms have opposite signs. And so that's the situation of the staggered chiral Hamiltonian. So with that, I want to ask myself, let's just focus on the case of just a chiral term and ask yourself, how do you make these terms happy? Well, the mixed product of three spins is just the volume that is of the parallelepiped that is spanned by these three spins. So if you want to extremize it, you just want to put them, to make all of them perpendicular to one another. Now, of course, that extremizes that, because whether or not it's +1 or -1 depends on whether or not the three spins form the right or the left coordinate system. And so we can make it +1 or -1. Now, and this already gives you an idea that perhaps we should be looking at the states that were very similar to the coplanar states of the Kagome lattice, because perhaps now the special role will be played by the states where somehow all spins in your system choose to point along the same three coordinate axes, if you wish, x, y, and z. So we call them the triaxial states, and they play the same role as the coplanar states for the Heisenberg model. The only difference is that instead of telling you like the direction of spin in the plane being marked with red, green, and blue, now it's the three axes x, y, and z that I marked by the same three colors. And so the arrangements, well, you can still identify the √3 by √3 and the q equals 0 state. But of course, now the difference is that I still have this degree of freedom of whether or not a particular spin points in the positive x or negative x direction. And that is an important degree of freedom, because after all, I must arrange the correct handedness of my three axes around a particular triangle. And specifically for lambda equals 1, that's the situation where I want all triangles to have right-handed triads, so that, for example, if I go, so what it means is that if I traverse my triangle in the counterclockwise direction, the order in which the axes come should form a right-handed coordinate system. So for example, this would be x, y, z. That's good. But all of these triangles must have the same handedness. So XYZ is the right-handed coordinate system. But now if I wanted to, and so it's this one, so XYZ. But now if I wanted to look at this triangle, going from XZY would clearly be the left coordinate system. And so one of them or three of them must come with a minus sign in order to fix that. So you see that, for example, the √3/√3 state for the uniform case, that is when all triangles should have should form right-handed triads. The uniform state is, like, let's say all pluses, is impossible. So I must have, so all downward-looking triangles, you know, like if I arranged all the top line of triangles as plus, 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 I immediately have to start putting minuses here. And so then you just go from there. Now, in fact, there are many ways of arranging plus and minus signs that still satisfy this condition, the ground state condition. But I want to say that you can count this number. I don't want to derive it for you. It's pretty simple. That's the number of possible sign arrangements. But it's important that no matter which triaxial state you choose, that is the state that I can do with three colors, the number of signs that satisfy the ground state condition is exactly the same. And so there is no statistical bias between different states that comes from being able to arrange the signs. So they all come with the same exact number of sign arrangements. Now, I should point out that there is still a notion of Weathervane modes, and it goes exactly in the same way as before. So you choose a line, a loop on your lattice that contains only two colors. And remember, these are, in this particular case, these are Z and X directions. That means that all neighbors are pointing in the Y direction, and you can just rotate these two, irrespective of whether we're plus X or minus X and plus Z or minus Z. We just rotate them around the Y axis, and that's also free. So the Weathervane modes here are very similar to the Weathervane modes in the
So your yellow line has greens on as well. Should it only have blue?
Oh, sorry, I jumped the gun. This is not a Weathervane mode. This is something else. Thank you very much. So the Weathervane mode will only contain two. This is something else that I wanted to make point of. So what I wanted to say with this is that you choose any line that passes every triangle only. Well, it doesn't touch it, or passes through a particular triangle touching two of its spins. That means that a line doesn't have any acute angles. A loop, and you can flip the signs, and that's still as good an arrangement of signs as before, because every triangle either had two of its axes flipped or none, and so that preserves the handedness. Thank you very much for catching this, because I was
trying that the hexagons are they obey what you said earlier about.
Yeah, because this is the √3/√3 state. Yeah, sorry, I have a very similar picture when I talk about the Weathervane mode. But thank you very much for catching this. This was a point that, you know, how I can actually play with these signs, and this Z2 degree of freedom, whether or not the spin points along the axis or in the opposite direction, will actually play an important role later. And so thank you very much for catching this, and hopefully, yeah. So this is just the story. So you draw a loop, you flip the signs. That's still a good ground state. All right. So now what I wanted to say is that there are also Weathervane modes, and the Weathervane modes now should only affect two rather than three colors. So this is a different state, and in a different state, of course, what you do is you just choose you choose a line and you rotate them from what used to be just green and blue to so the red ones are out of the plane, sort of either, you know, out of the plane, and you just rotate these by some arbitrary angle. So that's the Weathervane mode. So now it only affects the two colors. Does that make sense? Very similar to how it is on the Heisenberg Kagome. And notice that rotation by pi simply flips their sign. So rotation by pi is equivalent to just flipping the signs of the, in this particular case, it would be whatever X and Y axis. That's a special case. This is something that we'll call the pi Weathervane modes. And the pi Weathervane modes are special if I look at the semiclassical physics of them. If I actually do the either Landau-Lifshitz or Holstein-Primakov approach to large spins, but I actually allow for the finite h bar. It turns out that the pi Weathervane modes are special in a sense that it can be gauged out from the semiclassical equations of motion, which is not an obvious fact, because something that you might remember from quantum mechanics, so, that is flipping a spin is an okay thing to do classically if you just think about this as a vector, but it's not an okay thing to do if you deal with quantum mechanics, because it's not a canonical transformation. Because that would not, if you flip all three components of your spin, that does not preserve the commutation relations. And so for that reason, for example, the spin waves are different in a ferromagnet and antiferromagnet on a perfectly unfrustrated square lattice, where you think that the two are equivalent to one another if you just flip every other spin. And classically, that works, but semi-classically, it already doesn't, and results in different spectrum. But here, if you perform this pi Weathervane modes, that is still an allowed, so it turns out it can be completely gauged out. So it works semi-classically. So this was about the ground states and the Weathervane modes, but what about harmonic zero modes? Those were the ones that were really important for selecting a subset of states. And here it works like this. That's not my phone, is it? Okay. So the way it works here is if you decide to play with so what you should try to do is, in order to get a mode that is quadratically soft, that is harmonically soft, but costs you some energy in the quartic approximation, what you should try to do is roughly the same thing as before, and that is take two incompatible Weathervane modes, that is, for example, this and that, or this and that, or in the case of √3 by √3 states, pick any two lines that go through, and try to rotate them by the angles alpha, beta, and gamma, and the correction to the, once again, we are back to the perfectly classical Hamiltonian, so I'm not doing anything related to any h bar. So the correction to the energy looks like this. So it's actually quartic. You see that it contains both angles so in this particular case, you can do it with all three incompatible Weathervane modes. So you get this quartic correction. But the important thing is that you only get this when you try to excite genuine Weathervane modes, when each of them is a genuine Weathervane modes, which wasn't the case for the Heisenberg case, where sort of you could do it for any hexagon, irrespective of the fact whether or not it was a Weathervane mode or not. Here, the geometry is different because the spins don't lie in the same plane. They point in the directions perpendicular to one another. So the naive argument I gave you before simply doesn't work here. And so here, you actually get something interesting. So the number of these quadratically soft but quartic modes is actually given to you by the number of independent Weathervane modes that you could originally had in your system. And we know that different states have different number of Weathervane modes. Specifically, √3 by √3 has them in every hexagon, whereas the Q equals 0, this one, only has a subextensive number of them. And so it's therefore very suggestive that the √3 by √3 state in this particular case should win hands down without sort of any necessity of going to the higher orders. And this is what I basically said, that the √3 by √3 state should actually win. So now, what about the situation when you have a mixed Hamiltonian? That is when you mix in the, so far I was talking about the pure chiral situation where the three spins should be perpendicular to one another. Now, if you mix in the Heisenberg term, what it does, there is actually a continuation between the state in which all three spins are orthogonal to one another and the situation where they just lie in the same plane at 120 degrees to one another. And the way to visualize it is to look in the direction of the body diagonal and just try to flatten the spins, where this flattening angle actually varies continuously as a function of the parameter parameter lambda that tells you where you are in the space of the Hamiltonians. But the interesting thing is that now you lose the Z2 degree of freedom that could help you fix the chirality if the chirality of a particular triangle was wrong, because now the spins are no longer perpendicular to one another. And if you flip one of them, they don't form the ground state anymore. I don't know if so it's easiest to imagine going all the way to the Heisenberg. If you now decide to flip one of these spins, clearly that's no longer 120 degree of freedom. And so now the number of ground states actually is severely restricted. And it's restricted, for example, specifically the √3 by √3 state is still possible if the chiral interactions are staggered. And it's not a ground state if the chiral interactions are uniform. And the Q equals 0 state is the opposite. It's still a good ground state if the chiral interactions are uniform, but it's not a good ground state if the chiral interactions are staggered. And so with that, I just want to show you some results. And these are the results of the same old specific heat that, remember, was an indication of the onset of order by disorder on the Kagome lattice. So this is the result of the Monte Carlo that Bussen has done, this is the specific heat versus the interaction parameter lambda. And just to remind you, so this is the pure Heisenberg case. This is the pure chiral with uniform interactions. This is the pure chiral with the staggered interaction. Now, for the pure Kagome, for the pure Heisenberg, you get this. So this is 11/12. That's what you deserve if you have the onset of order by disorder. So that's what we already saw for the pure Heisenberg. And anywhere in the negative lambda regime, where the √3 by √3 state is a ground state, you actually see the signatures of that. So basically you get the same specific heat all the way here. Now, on the other hand, if you go to the uniform regime, I just told you that everywhere aside from the point which is purely chiral, where you can fix the issues with chirality by just flipping some spins, I cannot do it here. And here you don't see the onset of order by disorder. In fact, the number you get is close to 23/24, and you think there is some significance of that. But it turns out the only significance of that number is that this simulation was done on a finite size system. And even though the number of Weathervane modes for the root, so this basically shows you that the Q equals 0 state is selected. That has a sub-extensive number of Weathervane modes, but of course on a finite size system there are still these Weathervane modes. You can count them and you can see what is their contribution to the specific heat, and you end up with this number 23/24. That's just a finite size effect. One thing, and so it crashes back to 11/12 right here at the chiral point, but it's not there anywhere else. Now curiously, there is this peak somewhere, and you might ask yourself whether or not it's an artifact of anything. And in order to ask that, to answer that question, we also looked at, I wouldn't call it the order parameter, but it's some correlation function that I don't even bother writing down here. It's the correlation function that is, so there are two correlation functions calculated here. One correlation function is the correlation function that is the yellow, is the one that is designed to be saturated at 1 if you are in the √3 by √3 state. And if you are in the Q equals 0 state, that's kind of the minority line. It doesn't crash to 0. So there are two lines here, the line at 1, and then there is this other line that is dashed. And so the two correlation functions are designed that if you are in the √3 by √3 state, then the corresponding value of yellow correlation function would be right here at 1, and the corresponding value of the other correlation function would lie on that dashed line, and vice versa. So what do we see here? Well, we see the √3 by √3 state here clearly because that's yellow saturates at 1. Now you kind of start losing the selection of √3 by √3 as you go towards the pure Heisenberg case. And in the pure Heisenberg case, remember everything, any coplanar state is as good, and so you don't get any particular preference of q equals 0 to √3 by √3. Everywhere on that side where I told you that now the √3 by √3 is not a good ground state, but the q equals 0 is, you indeed see the indication of q equals 0 state, whereas the other state disappears. So disappears means it's actually lies. The way these correlation functions have constructed, they don't crash to 0 if you're in the wrong state. But that's what they crash to. But then at the location where you saw the peak, something interesting happens. The two states switch. And this is, so after a little bit of thinking, we realized that this is the effect of order by disorder on steroids. This is the situation because you do this simulation at some finite temperature. It's not like infinitesimally small temperature. This is a finite temperature. And at a finite temperature, even though the √3 by √3 state is not a ground state, it still has lots of fluctuations around it. And since the finite temperature, you're supposed to optimize the free energy and not the energy. You see the situation where the state, which is not a ground state, is nevertheless dominating the Gibbs ensemble. So this is the q equals 0 state, even though it's a correct ground state, it's basically invisible in your statistical mechanics because there are very few. So the thermal fluctuations stabilize the state that is not a ground state.
So if the temperature went to 0,
so yeah, so if the temperature went to 0, you would expect this line to go to the right. But of course, it's basically impossible to do numerically because as the temperature goes down to 0,
so it's a funny order. There's an order of limits.
That's right. Yeah, it's certainly the order. Yeah, there is certainly an order of limits involved in that. But nevertheless, that's the explanation of that jump in the specific key that we saw. So that's a transition between these states. Now I should immediately say something that I should have said earlier. So everything I talk about here is strictly speaking crossovers, because there are no phase transitions that are allowed here by the virtue of the Merman-Wagner theorem, because we are working in a two-dimensional system where no breaking of a continuous symmetry is allowed. Nevertheless, if the system is large by finite, and that's what this indicates, you see, even in the case of, just to explain what I mean by this comment, think in terms of coplanar states in the pure Heisenberg limit. It would have been exactly the same story. What would mean if you look at your system on a large but not too large scales, you would find the coplanar order of spins. But if you walked far away in your system, you would find that the plane in which the spins are ordered actually is not the same plane as it is here. So in any finite system, you would find this finite, not sufficient, not too big system. You would find this coplanar arrangement of spins. But if you take a thermodynamic limit, this will wash. So that goes back to a comment of the order of limits as well. So that's so these are crossovers. These are not genuine phase transitions.
There's actually multiple things. There's the temperature going to 0.
That's right.
Lambda going to 1.
That's right. Yeah, exactly. So it's. But that's what it looks like in a finite system. So that's fairly large finite system, by the way. All right. So let me, if I still, can I talk for another 5 minutes or so? Yeah. I want to comment on, so that was the story about the thermal order by disorder. What about quantum order by disorder? Quantum order by disorder, as I explained, is instead of thermal fluctuations, you now worry about quantum fluctuations. What does it actually mean? That means that what you should do, you should evaluate the spin wave spectra. These are your harmonic, so the quantum version of the harmonic degrees of freedom, and each of them contributes a half h omega over 2 of its zero energy. So this is kind of like the usual Casimir story or something like this. That's the contribution of 0-point energy into the actual energy of your system. And so here, each spin wave contributes a half of its frequency into the 0-point energy, and therefore a state that has particularly soft spin wave spectrum around it would actually be energetically preferable, because the 1/2 of h bar omega that it contributes is smaller than it is for the other states. But now you worry about the entire spectrum, because I mean each of them contributes, so you just need to find the entire spectrum of the spin waves and integrate it over the Brillouin zone, and then the states that give you the smallest energy win in quantum order by disorder. Naively, you could expect that the thermal and quantum order by disorder result in the same states, but there is no theorem to that extent. In fact, there are counterexamples. There are not many, but they're known, where, because the mechanisms are somewhat different. Thermal and quantum fluctuations don't have to act in exactly the same way. And as I said, the way you analyze them is different. You do the spin wave spectrum and you analyze that, and this is the part that was done by my graduate student Jack Pitts. And so these are the examples of what you get for the q equals 0 state, for example, and depending on the parameter lambda. And here is something interesting. So the q equals 0 state, remember, is the state that doesn't have local Weathervane modes. And the spin wave spectrum shows some places where the spectrum of spin waves crashes to 0, but only does so completely. So you get a complete band at 0 energy only for lambda equals 0. That's the pure Heisenberg case, where I told you that the all harmonic modes just become quartic at that point. Everywhere else, you don't get that. You only get lines rather than, so these are something we refer to as grooved modes. On the other hand, for √3 by √3, you can just, by counting arguments, all Weathervane modes would produce a flat band in the spin wave spectrum. But it's not just a flat band that you care about all of them. So these are different cuts between different symmetry points in the Brillouin zone. I have to say that these are very involved calculations, because of course there is this, particularly at lambda equals plus and minus 1, where you have the Z2 degree of freedom, and that Z2 degree of freedom plays a role, because I told you that well, depending on how you choose these degrees of freedom, the Brillouin zone depends on that, the spectra depend on that, and so you cannot possibly probe all of them. And so what you have to do is you.
So for lambda equals 0, what?
Lambda equals 0 is the Heisenberg case. So you just have a complete flat band at 0. That's just, so what is shown here is just the lowest band.
In the first line.
So that's the 0 band. So this is the, this shows just cuts of all bands in along different lines, and I cannot do a 3-dimensional plot. So a 3-dimensional plot would have all these bands. So these show just the lowest bands. These show all bands but cuts through the Brillouin zone. And you see that here you just have a complete flat band no matter where you look at the cut that corresponds to this lowest band. For the rest of them, you get 0 somewhere, and this somewhere actually it's these lines.
I would have thought if all harmonic terms vanish, then all bands are.
No, because you have, remember, you have 1 per hexagon, that's 1 per 3 spins.
Okay, so there's some direction which.
That's right. Yeah. So they only vanish. So one vanishes in the q equals 0, but the rest don't. And you have to calculate all of them, because that's how quantum order by disorder works. All right. So this is embarrassing. Right. So I want to very quickly explain to you that there is actually some interesting story that happens with the Z2 degree of freedom. Z2 degree of freedom is, remember, my decisions of whether to orient spins along or against a particular axis. And as I said, that it doesn't always result in the same equations of motion. It affects the size of the Brillouin zone, and so that's it becomes basically the project of finding all possible, calculating the spin wave spectra for all possible arrangements, even for a particular, let's say, Q equals 0 state, simply becomes impossible. But what we try to do is we try to actually follow the logic that was introduced some years ago by Chris Henley and try to understand the effect of these. So Chris Henley introduced a completely different subject in the context of pyrochloromagnets. Those are another subset of very famous frustrated magnets, but we try to apply it here. And in order to do this, what you want to do is you want to derive an effective gauge theory, and for these Z2 degrees of freedom. And let me try to just sketch how it's done. So first thing first, what I want to do is I want to go from my lattice to just in traditions of gauge theories where the degrees of freedom live on the links rather than the sides. I just draw a honeycomb lattice where the link of the honeycomb lattice. So this is just a cultural step. It has nothing to do with the physics, but that's how people think in terms of gauge theories. So now the links of the honeycomb lattice has the old spins, and that's what I'm dealing with. And now, of course, I want to just do away with the designations of X, Y, and Z and just stick with 3 colors. And now I just made the lattice a little bit bigger. And now I want to do one thing. So I have this Z2 degree of freedom that lives on each link, and whether it's plus or minus will be designated by either leaving this line, a particular line dashed or solid. So that's my designation for whether it's plus or minus. So for example, this would correspond to, so let's say the solid lines are -1s and the dashed lines are all +1s. So the background is, let's say, all +1s. Okay, so here is like -1, -1, minus, and so on, and everything else is +1. This is a single plaquette where I flip the signs of these degrees of freedom. And now let's try to bring some order to all these pictures. And what I want to do is I want to define a flux that is the product of the sigma z degrees of freedom. So these are my plus or minus 1 degrees of freedom around a particular hexagon. So in this particular case, well, all of these are -1s, but the flux is still positive. But so how do I detect this flip? Well, even though the flux is still positive for that hexagon itself, it's actually negative around it on all the neighborings, because all neighboring hexagons have just one sigma flipped. Yeah. Yeah, I'm almost there. So now this is the Q equals 0 state. Remember that flipping all spins along a line was a pi Weathervane mode, and that should cost me no energy, but it also produces no flux with this definition of flux. And if I wanted to do something like this, where this line looks like a Weathervane mode, this line looks like a Weathervane mode, and the only deviation from a Weathervane mode is here, well, the only places where I get these negative fluxes happen around that point. Everywhere else, it's fine. So this somehow is a very local degree of freedom that tells me that I'm doing something non-kosher in terms of the semiclassical equations of motion. And so with this, you actually can expect that the 0-point energy in different Q equals 0 states will depend on where you put the fluxes and how they interact. For the √3 by √3 state, on the other hand, every hexagon is a pi Weathervane mode, and so that should cost absolutely no energy if you flip them. That's all should lead to the same exact 0-point energy. And so what we find is the dependence, so I mean, we did some simulations for different, or some calculations for different distribution of fluxes, and what we found, the dependence of energy on the flux density, and you see that it's roughly following the straight line depending on just the flux density. And no matter what you do, these kind of look very similar for the so this is lambda equals -1, this is lambda equals +1, so staggered and uniform states. And they look similar unless you look at the y-axis. The √3/√3 state here is below, and here you don't even see it, because if I were to put them on the same plot, that's how they would look. So for the staggered case, this is the √3/√3 state. This is the Q equals 0 state, that is much higher and with smaller slope. This is the uniform state, for which there is a much stiffer competition between the two, but the √3/√3 state still wins. And remember, that one is independent of flux, because that's the story there. So the upshot of all of this is that, as far as we can tell, the √3/√3 state still wins in quantum order by disorder, both for uniform and staggered case from this. But let me just spend 30 seconds on thinking a little bit more about this gauge theory that I introduced. And that is like the normal gauge theory, the effective gauge theory would look like something like this. So this is the term, this is the term that is, I would call the vertex term, that just enforces the correct chirality of the spins around a particular vertex of my honeycomb lattice that used to be a triangle of the Kagome lattice. This is the term that we actually investigated. That's the chemical potential times the density of fluxes. And in principle, you should allow for the interaction of fluxes, not that we studied it, because you see that the second term does a pretty good job by itself explaining what we see. That's what it would look like for the Q equals 0 state. That's the effective Hamiltonian in terms of the Z2 degrees of freedom. What would it look like for the √3/√3 state? Well, for the √3/√3 state, as I argued, it's completely flat. So that means that there is no term that depends on the density of these fluxes. But then you can ask yourself, well, what other terms could be there? And one term you can write that actually commutes with this is the term that simply flips these degrees of freedom around the plaquette. Furthermore, if you actually did the 1/s expansion, you would invariably get a term like that in your effective Hamiltonian. Now, those of you who have heard of the Kitaev storic code would recognize this as the Hamiltonian of just that, of the Kitaev storic code that has vertex term and plaquette terms. These terms commute with one another, so you can solve this Hamiltonian exactly, and it's an archetypal Hamiltonian for the Z2 spin liquid with the, state with the Z2 topological order. This is not topological order in terms of the original spin. This is the spin liquid in terms of these emergent Z2 degrees of freedom, but nonetheless. So this is suggests a semiclassical route to something that falls into the category of spin liquids or topological spin liquids. So with that, I thank you very much for your attention, and I probably already told you much more than I should have. Thank you.
So one very trivial thing that I guess, so am I right in thinking that the Kagome is sort of dual to a honeycomb then?
Well, define dual. So what happens if you, like, if the center of triangle becomes a site of the honeycomb?
Yeah, okay.
So a triangle of the Kagome serves as a vertex on a honeycomb lattice.
So this is just an impressionistic thing. That what you were saying about Weathervane modes reminded me of cluster algorithms for things like the Fox model.
Yeah, definitely.
So is it the same basic idea that there's some sort of, you could think of it in terms of a different degree of freedom that will flip whole domains?
Right, exactly.
And if you were trying to do a Monte Carlo exploration of the whole phase,
that's right,
you do much better with that than you do with local updates.
That's right. That's right. Yeah. So for exactly. So for the Potts model, basically, if you, I mean, so Potts model is already like these three colors, right? So there are no continuous degrees of freedom. So it's, I mean, so these three colored states I could as well just call the Potts states. So that's the situation where you want the three, the three neighboring sites all to have different color. And then what you're saying is basically equivalent to what I call the pi Weathervane mode here, where you just, no, it's actually not pi, it's pi over 2. That's, that you pick a pi Weathervane mode if you flip the sign, and the sign doesn't even exist in this Potts language. So it's, but in the Potts language, what you want to do is you want to do this quote unquote Weathervane mode. So you choose a line that contains spins of only 2 directions, 2 colors, and you simply exchange these colors along that line. That keeps you in a state that is, if you started with a ground state, you're still in a ground state, and so on. So yeah, that's at that level, these Weathervane modes are indeed they're designed to be this sort of cluster transformation that costs no energy. And so, yeah, in Monte Carlo, that's what you generally want, because that allows you to do something highly non-trivial and not be rejected by the metropolis weight. So
are there materials where these chiral interactions are very dominant?
Not that we know. So there are some ideas of how to do that using cold atoms. But that seems to be anytime you come up with a crazy Hamiltonian, somebody tells you that, oh, maybe we can do it in cold atoms. So people look at this. So, well, first of all, the most interesting story that I told you is when the interactions are purely chiral. So you can, of course, expect chiral terms as some correction to the Heisenberg terms, but even that comes with a condition, because remember the chiral term breaks time reversal symmetry. So either you have to break it by hand, I don't know, by putting your magnet in magnetic field. So if you look, for example, at the situation where you have super exchange mechanism in the presence of the external magnetic field, then it's perfectly allowed as the next term. So normally super exchange would generate Heisenberg term, then there would be some ring exchange terms that would involve the even number of spins, because those don't break time reversal symmetry. This one does, and so in principle, if you somehow break it spontaneously or by hand, that might emerge. So anything that is not forbidden will eventually be found, of course. But one reason we even looked at this model, as crazy as it is that it turns out this model has a very interesting behavior in the quantum limit, that is spin 1/2. And that people have found that there are, depending on whether you look at the uniform or staggered case, you find quantum spin liquids in both cases. They're very different. In the uniform case, you find the Kalmar-Laughlin state, which is the chiral spin liquid, which is, for those who know what I'm talking about, it's the spin liquid that mimics the quantum Hall spin state. And in the other limit, in the staggered limit, you actually find the gapless spin liquid with a Fermi surface and whatnot. These are mostly numerical studies. And so this whole project started from just, okay, let's see if this is what the system does in the quantum most case. Let's ask ourselves what it does on the opposite side of where h bar is as little as we can imagine, including 0. But I'm not claiming that that describes any particular material.
The spin 1/2 case is that, I don't recall details. Is that somehow related to this model that Fredkin and collaborators studied a few years back?
So I'm familiar with the papers by Bella Bauer, Andreas Ludwig is on part of that, Simon Trebst, actually. I mean, so I was looking at these models out of curiosity. The fact that Simon Trebst started looking at these models, the classical version of this model, was not incidental, because he was actually involved in the quantum version of that.
I think I'm thinking of a different paper.
So the other paper I'm aware of is by, and I will mix up the authors, but one of them is Annie Nilsson, who and Ignacio Serra might be a part of that. Hernan Serra is another person there, where they basically did a CFT construction of these states. But that's a little bit more involved. But that's also that relates. I mean, on some level, it's a complementary paper to the Bauer et al. Paper where they did the. Fratkin, I'm not sure which paper you're referring to. Well, thank you very much.
Thank you.